First of all, thank you very much for giving us the chance to share our works and discuss with other scientists and see their opinion. So today my name is Mouad Fattouhi from University of Salamanca. I'm a PhD student working on magnetism and electric field effect European project under the supervision of Professor Luis Lopez Diaz and Eduardo Martinez. So today I will present to you our latest work about electric field control of magnetic skyrmion dynamics in artificial multiferroics. Let me first start by exposing the motivations of our work. So as you know, skyrmions are nanoscale topological structures derivable using manifold methods. Regardless the driving force of a skyrmion, it exhibits a tilted trajectory from its principal trajectory imposed by the driving force, and this is due in principle to the precessional nature of the magnetization dynamics, yielding on a geotropic force pushing the skyrmion far away from the principal trajectory. So this phenomenon was named as skyrmion Hall effect and studied widely by theoreticians and experimentalists, and was considered as the main problems in the way to construct devices based on straight motion of magnetic skyrmions in racetracks. The question is, are there any solutions for this problem? Of course there are. Scientists were proposing many solutions. For example, systems like narrow channels where the skyrmions could experience some forces from the edges that could be helpful to maintain the skyrmion going on the center. Or for example, the other systems with antiferromagnetic coupling, such as ferrimagnets at angular momentum compensation, antiferromagnets and synthetic antiferromagnets were very useful also to suppress the skyrmion Hall angle. However, methods providing like more versatility in controlling the skyrmion Hall angle or the skyrmion Hall effect will be very beneficial to the technological applications. Let's see if we can do something providing more versatility on controlling the skyrmion trajectory. So our idea is to propose a device based on a thick piezoelectric substrate. On top of it, we have two electrodes. Between them, we have a magnetic multilayer based on a heavy metal, ferromagnet, and an oxide, suitable to stabilize magnetic skyrmions. So first thing we did is to characterize the piezoelectric response of such device. To do so, we used FEM simulations based on COMSOL, and by exciting the two electrodes using 10 volts potential, we get the field pattern shown in this figure. So as you can see, the field is highly non-uniform, going from negative to positive, and then if you can see it, it will go inside the heavy metal. This is because the heavy metal is a conductor of nature. So to see clearly how the field is non-uniform, we plot the ECL component of the field along this line, and then this plot shows how the field is changing the sign from negative to positive. Even if, for example, the center of the field curve is looking so flat, but if you do magnification, it's not flat, of course, and could be approximated like a non-linear gradient. So this highly non-uniform field, of course, will induce a highly non-uniform strain in the piezoelectric layer, which will be transferred to the ferromagnet. So this strain profile is due to the dependency of the strain to the field via the dielectric matrix. So let's see now the effect of this strain gradient on magnetic skyrmions. The idea is that we have a skyrmion driven in principle using spin Hall effect, using current. So in principle, using Thiel's model, we can describe the skyrmion dynamics as follows. The skyrmion experiences a force due to the current pushing the skyrmion to move straight. However, due to its topology, there is an intrinsic created force pushing the skyrmion outside of its principal drive. These make the skyrmion move in a tilted trajectory. Imagine now that we excite the electrodes shown in the previous slide, so we will have a gradient of the strain. This gradient will yield on a force, a second force on the skyrmion transversally applied, which will compete against the Magnus force due to the current. Using Thiel's model, we were able to derive an expression for this force. So this force was depending importantly on the strain gradient, the elastic constants, and the magnetostriction, the saturation magnetostriction. The only parameter which is tunable in this case is the slope of the strain, which could be tuned just by applying the voltage or changing the distance between electrodes. Besides this, we performed also micrometric simulations based on MUMAX. We modified MUMAX by including an extra contribution of the Magnetoelastic field to the LLG equation. So the parameters used for simulations were those of oxides, cold iron-borne heavy metal materials. As a result of the force due to the strain gradient, as you can see here, the skyrmion trajectory is perfectly tunable using just by applying the proper voltage. So we can move and locate the skyrmion wherever we want using this elastic force. Here you can see that this elastic force contributes to reduce the skyrmion hole angle, or even to suppress it totally, or to make it negative. It means that you can move the skyrmion in the right or in the left of your field. So using the model, we were able to derive a condition that will govern the case where you have perfect compensation of the skyrmion hole angle. And as you can see, this condition links the strain gradient to the current. So means that if you have an applied current and you drive the skyrmion, it's enough to apply the proper voltage, which could compensate the Magnus force due to the current itself. So simulations and the model were predicting more or less the same behavior. This means that the model was capturing very well all the features of the dynamics in our case. Not only we can suppress the skyrmion hole angle, but also we have a good feature that we can increase the longitudinal velocity of the skyrmion using this new force. And this is due to the fact that we suppress the drift component of the velocity. This means that we enhance the straight motion of the skyrmion in the sample. Up to now, I was presenting the results for an ideal sample. Now let's see if this method works in presence of impurities like magnetic disorder in the system. So to do so, we modeled disorder in our simulations via Voronoi tessellations, imposing a random distributions of grains. Each grain, the grain size was 5 nanometers, and the magnetic properties between grains was supposed to change by 2% percentage. So the results are shown here. The same behavior found for ideal samples was present also for disordered samples. And then you can see that the velocity increases and also the skyrmion hole angle decreases.
To interrupt you, you have 1 minute left.
Yes, of course. We know, of course, that disorder decreases the skyrmion hole angle, but we are mainly interested in this trend. So the strain was working perfectly to reduce the angle even in presence of disorder. So here I show animations. The first one is without strain. The second is with strain, and it's clear from these animations that the strain works perfectly to reduce the skyrmion hole angle in presence of disorder. So as conclusions, I was showing that electric field induced strain can be used to tune the skyrmion trajectory. The skyrmion hole angle can be controlled efficiently via strain under realistic conditions, and our method will allow to increase the maximum achievable velocities for racetrack memories, skyrmion-based racetrack memories, since we can inject more current before that skyrmion annihilate with the racetrack edge. So to sum up, I would like to thank the funding from the European Union via Magnify project, and my collaborators, of course, the members of my group. And then you can see here that finally we could few weeks ago meet in person within the project. And thank you for your attention. And if there are any questions, I'm here to reply.
So I have a question that you mentioned the outside layer. So the outside layer for the skyrmion hole effect is clear or not?
Sorry, I cannot.
So the outside layer is good or not for the skyrmion Hall effect?
The oxide layer.
Yeah.
Can you repeat please the question because I cannot hear you very well.
So the outside layer here.
Okay.
Yeah, the outside layer is good or not for the Hall effect?
The oxide layer in principle is used to induce or to induce some perpendicular anisotropy that helps to stabilize skyrmions, but it has no effect. In principle, it has no effect on the skyrmion Hall angle.
Okay, okay. Thank you. Any question? So let's thanks the Mouad again.